Hello, this is A Squared at mathandstuff.com. The topic for today is angle measure, including history and links to material I use in class. Mathandstuff.com has as its last link the link to mathandstuff.com on video, on which one might find the videos ready for use at this point in time. The topic for today is listed under pre-calculus and includes a web page, a link to a web page, video of the page, a PDF file for the page. You might want to download it now. You might want to download it later. You might not want to download it at all. Also included are separate video, is a separate video for making a hexagon and the Sketchpad used in that video. This material and all the rest of the material posted on the mathandstuff.com site is free to anyone who wants it. Download it, use it, edit it. You mess up, download another copy. I'm going to begin. If you're not ready, you might want to freeze the video. I'm going to the web page. The web page on angle measure starts with a disclaimer. This is research I have done. I'm not a historian, I'm a math teacher. So the material that you see is because I've researched it and referenced it on other pages. I have no footnotes on this one. I do make comments with authors and web pages listed. Other history, you might want to do your own research and start with pages that I have listed. Again, this is the video. You can download it from here. The PDF file, I have mine ready. I have notes on mine. So we start. A number is a thought. Early societies and primitive ones until recently didn't even write numbers down. They used words or pointed to body parts to communicate an idea. You'll notice on this one, on this hand, the numbers are 1, 2, 3, 4, 5. But on this version, the thumb is not included. That's used for a pointer for counting the pads on the finger. 1, 2, and 3. Here, 1, 2, and 3. And down here, 1, 2, and 3 the other way. When you get lost, as I just did, go back and find where we were. Web page, there we go. It's all sitting there. If you get lost, freeze it, freeze the video, go back and find what you want. As the human race evolved, their numeration systems and computation devices also evolved. These are early ways of depicting numbers. Once people stopped pointing at body parts in a certain society, they were able to write them down Notice Roman numerals are base 10, and you'll notice there's a 5 here. There's a whole dialogue on the history page about that. Greek and Roman use very similar symbols. Hebrews, ancient Hebrews did also. The Egyptian and Greek were additive systems. Chinese is a multiplicative. Later, the Roman and Greek are decimal. But the thing I want you to note is the powers of 2, because that's what the Egyptians were thinking when they did computations. And I think I can close that. Oh, no, lost again. Go back to here. Go back to here. Okay, another source I have for you, 2 textbooks, 3 textbooks, really good resource stuff. Menninger is just phenomenal on counting boards in the Middle Ages. These are on African counting. Over time and in different locations, angle measures also varied and changed. The Egyptians built the pyramids, yet they counted using an additive system, which if you've never worked with a board to do counting, you can't appreciate it. Once you use a counting board, you will appreciate an additive system more. Multiplication and division were binary. They built the pyramids, and yet their measurement was with cubits, palms, and fingers. Well, what's a cubit? That's a cubit. That length. Fingers, I'm not going into. You get the idea. If you want to find out, use the link. Now, I'm sure if you know anything about Egyptian, ancient Egyptian, you've seen that picture before. Do you remember what it means? Did you ever really learn what it means? Most people don't know. I'm going to click on the image. That's what it means. The most important sense was smell. My guess is if you wanted to stay alive, you have to stay away from smelly things. Sight, you should be aware of where you were. Hearing, thought, touch, taste. Here's the story. I'm not going over it. Back to angle measure. Powers of 2, really important. For the Egyptians, they didn't even bother saying the word angle that I could find. That doesn't happen until the word angle doesn't happen until the Greeks. Yet they used their computation to indicate the measure of an angle. They used a fraction, what we would call the ratio of vertical length to horizontal length, which we call slope or tangent. That was it. They did just basic stuff, right? No way. They also computed sine, and they called it a half chord. A half chord indicates much more geometric understanding than we have. Here's another Sketchpad that I'm just going to download and open, and we're not going to do much on it. I think I want page 10. A half chord, what's that? A half chord is, here's a whole chord. A half chord, because it's symmetric, is just this segment. We'll call it BP. And notice, here's the arc on the circle. If you wanted to compute this arc length, you could squeeze it between a piece of the tangent and the half chord to get the arc of the length of the arc. My point in showing you this was to show you what a half chord looked like. We don't need it. I'm getting rid of that. The Sumerians, Babylonians, developed degrees, minutes, and seconds. You've seen that before. Where did the 360 come from? 360 is really nicely factorable and divisible, and here's some divisibility tests. It means it divides evenly, but the Babylonians and early civilizations, they looked at prime and composite 20,000 years ago. That's big stuff. But is that where they got the 360? I don't think so. I think, again, they did it more geometrically. I'm going to link to a Sketchpad here. And I think this one's listed, but I'm opening it anyway. We want to look at where a hexagon comes from. One might use a compass if it's a small circle, small hexagon you want to do, or if you're building something big, you might want to use a rope. I believe that's how they built Stonehenge, using that. I believe that's how they built Göbekli Tepe. If you don't know what that is, go search on it. You also need a straight edge, which you could use a ruler. Just all you have to do is mark the length, the edge. You don't need to get fancy with the numbers. It doesn't make a difference. The point in this is to show you, and I give you instructions to show you how to construct a hexagon. Notice 60, 60, 60, 60, 60, 60 adds up to 360, and there are 365 days in a year. So we're going to start with building a circle, and I'm going to start with a center and a point on the circle. Then I'm going to do it backwards. I'm going to build another circle. I'm going to start with the point and go out to the center. Well, I now have two important intersections points. I'm going to mark both of those. And I'm going to do, and it did it for me. It built two of the intersection. I got to do it all once. I now want to show you, and I am sure the ancients knew this. That's a segment. I want another segment. I want another segment. No. And there you have an equilateral triangle. Just by using circles. Beautiful stuff. Well, I don't want the equilateral triangle. I want to make a hexagon. So I'm going to hide this circle. Okay, I now want, and I'm just going to mark. No, I want a show point. It's already there. I now want to make more circles. I'm going to start with a point I have, and I'm going to go to that one. Now I'm going to do that again. This time I'm going to take another circle, and I'm going to go there. I'm going to mark the intersection. I'm going to do it again. Make a circle. Mark the intersection. Make another circle. Mark the intersection. I'm going to hide what I don't want. Hide it, hide it, hide it. Yeah, hide it. And this one. So now I have what looks like a bunch of dots. But now, what do those dots do? They make a hexagon, a beautiful regular hexagon. I'm going to get a little more fancy. Whoops. And it really doesn't matter what size your hexagon is. The central angles will always be 60 degrees. They'll always add up to 360 as long as your hexagon is regular. One more thing, now that I have a big hexagon, if we called that the radius of the circle, then a diagonal would be 2 radiuses long. I'd like to now have you consider around the polygon compared to a cross. The triangle is not listed because a triangle is missing something. If we want to compute a round versus a cross for a triangle, we don't have an across. There's no diagonal in a triangle. The smallest number of sides that has a diagonal in the polygon is a square, a regular polygon here. That ratio of a round compared to a cross for all squares is 2.825 or thereabouts. For a hexagon, it's 3. That's a really nice number. It comes from 6 sides, and each of the sides was the same as the radius. We found that out just a minute ago. 8. The ratio is 3.06. 12-sided decagon is 3.105. 16agon, I don't know the name for it, 3.12. Another idea I'd like to point out while I have something that moves is inscribed and circumscribed. And I think I can make this one bigger. Well, I thought I could find a... All right, it's fighting me. We're not going to worry about that. There we go. I can make it whatever size I want, but I want one of the hexagons to be touching on the outside of the exterior of the circle, and I want one of the hexagons to be touching right on the circle, so that I have a circumscribed and an inscribed hexagon. We don't need that anymore. And again, if you want to play, it's right there for you to download. So my position is that the Babylonians, the Sumerians contributed 60 degrees towards angle measure. I think that was really important. There is a video on what we just went over. I'd like next to talk about the Greeks and the Romans. Again, all this was relative to angle measure. Greeks and Romans, here's a picture of a board. At least that's what I see because I deal with manipulatives. The historians that I've read on the web don't see the reckoning table. They saw a game board. What I see is I see one accountant on this side, one accountant on that side, and the judge up here to do the supervision of the computation. Here's information if you wish to know more about counting boards. I'm going to make the Greek and Roman contributions a bit bigger. The Greeks, the Romans actually contributed the word angle to human linguistics. It meant corner. Euclid's Elements was another really big contribution to geometry. Latin from the Romans as a language which scholars used really until the 21st century, they're still using it to name new elements, and not the elements as much as species. And in the Middle Ages, that's what they wrote in. Once the Middle Ages started to get a little lighter, they wrote scholarly things in Latin. They also, and it might seem trivial, but it's not, the Greek letters alpha, beta, gamma, delta, theta were valuable. You'll see a little later why. And pi, the alpha, beta, gamma, delta, theta were for angles and their measurement, the measure. So now we go on to pi. You'll find thousands of pages on pi. Here's a definition. There's a definition. Here's a definition of circumference. There's a definition of diameter. Think around compared to across, what we just looked at. Polygons, perimeter, diagonal. Where a circle has around compared to across, it would be circumference compared to diameter. A polygon around compared to across would be perimeter compared to diagonal. Again, another look at square, hexagon, octagon, and decagon. Around compared to across. Around compared to across. Around compared to across. Approximate pi using the perimeter of a dodecagon. Now, I wrote this out, but it's trivial compared to what the Greeks did. I think it was Ptolemy drawing in the sand, measuring things in the sand. I could be wrong, but I think it was Ptolemy, one of the Ptolemies. Here's a dodecagon. It's 12-sided. Notice I have the inscribed and circumscribed hexagons, and there's your circle. So the around compared to across for a dodecagon, you may want to skip this. You might not want to skip this. I really felt it good. Here's the 60-degree angle that you remember from the Sketchpad. If you bisect it, you get a 30. That gives you a 30, 60, 90 right triangle. If you remember your trig, you know what the lengths of the sides are. The one opposite the 30 is the baby side. The double that is the hypotenuse, or the daddy side. And the middle one, the one between the smallest and the largest, is the mommy side. It's equal to the square root of 3/2. You don't know that. Just use the radius of the inscribed as 1. Use the Pythagorean theorem and you can get the height, the altitude. Well, that gives us this length. And now you wish this length to get that length. You have to use the sine law. I'm just going to skip that. I'm going to go back to where we were. Again, we talked about squeezing. Here's a picture of the squeezing. Here's the inscribed, the inner hexagon, and the circumscribed, the outer hexagon, all the computations there, but the circles between them, quote, between them. A circle is pi times the diameter. That makes pi equal to the circumference over the diameter. Around compared to across. For the circumscribed hexagon, the around compared to across, 2 square root of 3. For the inscribed, just 3. That means pi has to be between them. Pi is between 3 and 3.46. And that's only for a 6-sided figure. That wasn't good enough. Aha, it was Archimedes. Archimedes used a 96-sided figure. Now, the only way I can understand his doing this is he must have really drawn a big circle in the sand. I don't think it was on paper that he did it. I don't think they had paper. They had papyrus, they had vellum, but those were expensive things, and you couldn't get much accuracy if you're drawing a 26-sided polygon. I created this on the web. Here's the source. You don't remember what it is, you can always come back to this page. So that was important, I believe, for you to know. Now, here's a really good article on the history of pi. The man who invented pi. Invented in one sense, but as I talked about Göbekli Tepe and Stonehenge, those people, I'm sure, were comparing around to across. Here's her article. I've just linked it for you. And I'm going to close that. And I'm back to, I knew I shouldn't have closed it. Okay. Don't need that. Let's go back to here. Let's go back to here. Let's go back to here. Good review of what we've done. Good review. All right, we're back to pi. We went to the article that Patricia Rothman wrote. And this is, I think, extremely important. She quotes in medieval Latin and then in English. First, I can't read it. I'm going to try. Quintitas in quam con multiplicator diameter. Sounds like trivia. Oh, here we go. Provet. We finished it. Here's the whole quote. That's in Latin. Again, the language of the scholars. And it means the quantity which, when the diameter is multiplied by it, yields the circumference. What's that? That's pi. So the reason she said the man who invented pi is he used this symbol. The symbol replaced the words. The idea was known for centuries. The words were used after many centuries, but the scholars knew what the words meant. But The Greek symbol pi was introduced by William Jones in 1706. Now, if you grew up when I grew up, you heard it was Euler. It wasn't Euler who invented it. He popularized it. Why is that important? Jones took the step of making the symbol valuable for the idea that had been spoken in a Latin phrase and known, I am sure, way before that. Probably not spoken. They might have had a similar phrase. I don't know. I wasn't around then, believe it or not. So you had to have the idea. Then you had words to describe it. Then you had a man who popularized a symbol used by someone else. The reason the popularization was important was everybody needed to be speaking the same language. They had to know, look, let's just use the symbol pi instead of saying this entire phrase. That's important. Pi is known to be irrational and transcendental. If you don't know what those are, you can look it up in the dictionary, the one that's included on the website. Once again, once a symbol was popular enough so that all could communicate the symbol, the words and the symbol became useful and powerful. The math always existed. Now humans could conveniently speak of it. That's not where angle measure ended. Radian is the angle measure of today. Yes, we use degrees. Yes, they are important. But if you want to be perfectly accurate, you don't want a decimal rounding. Got us to the moon. But if you've seen the movie Hidden Figures, you'll know that the more decimals you have in your estimate, the more accurate you are. But that wasn't good enough for today. At this point in time, using the symbol pi gives you the exact accuracy. It's like a fraction's better than using a decimal. Pi removed the 22/7 as an approximation. Now we could use the exact number. All this is from Wikipedia. Yeah, it's a good source. Your English teacher might not like it, but this math teacher depends on it. The idea of measuring an angle by the length of the arc was already used by other mathematicians. 1400. That's way before Croat used it in 1714. If you look again on Wikipedia, it refers to the International Bureau of Weights and Measures. When I grew up, we called it System International, the metric system. It defines a radian as 1 radian corresponds to the angle for which the arc length and radius of a circle are equal. Radian is defined as being dimensionless. That means you don't have to put a unit symbol next to it. The remaining lengths, so I'm going to go through these and let's just look at that. radians. If you use the handheld calculator, you know you don't get a graph in degrees. Degrees don't help you. They're a limited measurement system. So you don't use degrees. You do use radians. And here's a curve with the sign drawn right here. That's about 3.14159. It's about pi. I don't use this kind of curve. I don't use this kind of plane. I use this one on which I have drawn the radian notation. I don't use this except for non-trig functions when I want just a sketch. I'm going to close that one. No, I know better. I'm going to go to angle measure, MP4. That's a whole video on angle measure. This page. Here's a whole video on radians and sectors. I do not intend to show you that. If you want to see it, this is what I do when I teach radians and sectors in a pre-calc class. It's too long to include here. Here's the Sketchpad for it. I hope you found this useful. That's all I have for you today. Have a good day.